Thanks very much. It's a pleasure to be here. Thank you very much for having me. So yeah, over the years since 2010, when the Continuous Delivery book came out, I visited many companies who've tried to implement these ideas of continuous delivery and DevOps, and I've heard many, many times, continuous delivery sounds great. What a fabulous idea. It won't work here. We're a bit different. So this presentation is a collection of stories and things that I've experienced over the years as I've tried to help companies adopt these ideas. But I'm going to start by defining continuous delivery. What is continuous delivery? Fundamentally, it's about being able to make changes of all kinds. Features, configuration changes, bug fixes, experiments, and being able to make those changes safely and quickly and sustainably. The goal of continuous delivery is to make releases and changes boring. You should be able to press a button and deploy a change at any time during normal business hours, and that should be fundamentally a boring activity. The exciting bit is the change in your user's behavior or the business impact of the features, not the deployment of those features to production. When we're doing software, fundamentally, we're doing two activities at the same time. We're doing a design activity, we're doing product design, and we're actually taking features and delivering them. In manufacturing and other industries, we separate these two activities. You do the design first, and then you do the development and delivery. In software, and particularly in the agile paradigm, we're doing both of these things at the same time. We're designing, and then we deliver something, and then we get feedback, and then we update the design so that we can build something that satisfies our customers and delivers value to our organization. But these two activities have two very different characteristics. When we're doing product design, that is very variable. You can design something, and that may take a long time for that design to come to fruition. There might be a lot of different steps to it, and many of those designs turn out to be bad ideas. Some statistics I'll present later on from Amazon. Most of the ideas that they have, 2/3 of ideas, turn out not to be good ideas. Whenever we innovate, there's risk. And if all your ideas turn out to be successful, you're probably not innovating. Innovation involves risk, so the outcomes and the estimates are very uncertain. However, when we're doing delivery, when we're taking changes and pushing them out to production, that's very different. We want that to be very predictable. We want that process to be automated as much as possible, and those outcomes should have very low variability. And so what I'm going to be talking about today is how do we achieve that stuff on the right-hand side? How do we make the delivery process very predictable to enable us to focus our attention on our innovation on actually designing products and features that are successful? Continuous delivery sounds like it's kind of a new idea, but actually a lot of the ideas are pretty old. Who remembers extreme programming and when extreme programming came out in 2000, 2001? Okay, a whole bunch of you. So a lot of continuous delivery is just ideas from extreme programming. We also took, Dave Farley and I, my co-author, we took a lot of ideas from Mary and Tom Poppendick's book on lean software development. That was the first book that really took lean philosophy and applied it to software development. Lean comes from manufacturing, and I'll talk about that more later. And then the third intellectual inspiration for us was Unix. And you might think that's a bit odd, but actually there's lots of very important and useful ideas in Unix that influenced us. So this is a quote from a paper that was written in 1978. So nearly 40 years ago, right? Number one, make each program do one thing well. To do a new job, build afresh, rather than complicate old programs by adding new features. So here you see the idea of microservices that we see today. Number two, expect the output of every program to become the input to another as yet unknown program. Don't clutter output with extraneous information. Avoid stringently columnar or binary input formats. Don't insist on interactive input. So this is the idea actually of a service-oriented architecture that we should be able to send data and receive data in a machine-readable format. Number 3, design and build software, even operating systems, to be tried early, ideally within weeks. Don't hesitate to throw away the clumsy parts and rebuild them. So this is the idea of agile in many ways. And number 4, use tools in preference to unskilled help to lighten a programming task, even if you have to detour to build the tools and expect to throw some of them out after you've finished using them. So this is the idea of a tool-based approach to software delivery. So these ideas are still fresh today. And many of the ideas we see in microservices, continuous delivery, come from Unix philosophy, which is 40 years old. The main 4 ideas, or the main 4 objections that I see to implementing continuous delivery are these 4. Number 1, people saying we're a regulated industry. Number 2, people say we're not building websites. Number 3, people say, well, there's a lot of legacy, and we can't apply these ideas in legacy environments. And then 4, the reason I dislike the most, are people are too stupid. And I've actually heard this. So this makes me crazy, and this session is kind of therapy for me, basically. So thanks for all being my therapist. However, these aren't the actual reasons. In my experience, if you look behind the scenes and you look for the causes of these objections, fundamentally it comes down to 2 things. Our culture sucks, and our architecture sucks. And those are really the 2 actual reasons why people find it hard to do these things. So I'm going to talk about culture and architecture and what we can do about that. So, number 1, we're regulated. Well, I like to show people this slide from Amazon when they say this. So this slide is from... Oops, sorry, that's the wrong slide. This slide is from Amazon back in 2011. So Amazon is about 1 order of magnitude faster than this right now. But back in, 2011, they were deploying, on average, every 11.6 seconds into production. So this is just their production environment. So they're making changes to production every 11.6 seconds, up to 1,079 deployments in a single hour. On average, 10,000 boxes receiving those deployments, and up to 30,000 boxes receiving those deployments. Amazon is heavily regulated. They're a publicly traded company, which means they have to follow Sarbanes-Oxley. They also process credit card transactions occasionally, and so they have to follow PCI DSS. So they have to follow regulations the same way that every other major public company in the US has to follow regulations, and yet they're still able to achieve these results. It required a lot of effort and investment to do this. They had to re-architect their systems completely from scratch, which took them 4 years to do in order to achieve this. So they invested a substantial amount of time and effort in achieving this. It was very hard for them to do, but they did it in spite of the fact that they're heavily regulated. I've been looking at high-performing companies for a number of years now, and running surveys and gathering data. And one of the things that I've been able to do with my team is find a statistically valid model for IT performance. There's 2 kinds of things we measure. Number 1 is lead time for changes. So how long does it take to get a change from version control to production? And then the second one is release frequency. How frequently can you release? And these 2 measures are measures of tempo or throughput. We also measure time to restore service. So when something goes wrong, when there's a failure or a service degradation, how long does it take you to restore service? And then change fail rate, when you push a change out to production, what percentage of the time do you have to roll back or do an emergency fix? So these are stability metrics. If you take only one thing away from this talk, this is what I'd like you to take away. High-performing companies do better at both. High-performing companies are not trading off throughput against stability. They are not moving fast and breaking things. They are actually achieving higher levels of both throughput and stability. They're going faster and building services that are more stable and safer and higher quality and lower cost. And this is not unprecedented. This is the same revolution we saw in manufacturing with the Toyota production system. Toyota didn't beat American auto companies by building cars that were cheap but were poor quality. They built cars that were cheaper and better quality, and they got to market faster. They fundamentally changed the game. And this is what we're seeing with DevOps and continuous delivery. Companies are changing the game and finding ways to build faster and higher quality and more stable and lower cost. One of the key techniques that enables high-performance IT is a concept from continuous delivery called a deployment pipeline. In a deployment pipeline, every change we make to our systems, whether that's a configuration change, an infrastructure change, a code change, any kind of change that impacts our systems, we run that through a series of tests. We run it through unit tests, we run longer-running acceptance tests, we do exploratory testing, and we tie every change together so that we can see the impacts of every change and get fast feedback on what the impact of that change will be. When you build a deployment pipeline, every change you make to the system, you can see the tests that have been run against it, you can see who's deployed which build to which environment, you can see the output from that change, you can see who authorized it, the timestamps. It gives you amazing information to be able to audit every change, where that change has been, what builds are in what environment. And actually, auditors really love this stuff. My colleague, Dave Farley, who co-authored Continuous Delivery, worked for LMAX, which was for a long time the world's highest performance financial exchange. And when Dave showed the auditors this stuff, the auditors loved it. This is much better than what you see in many companies in terms of change management. I had a colleague who worked for a large European electronics manufacturer, and anytime they wanted to make a change to production, they had to fill in a spreadsheet with 7 tabs. And in that spreadsheet, there was all these details about the change, and the developers would, when they wanted to make a change, they would copy the last spreadsheet and make a new copy and change a few fields and email it to a change manager in a different country. And the change manager would look at it, and if they weren't quite sure what it meant, they would call the development manager and ask them some questions. And if they liked the sounds of the answers, they would approve the change. And so the developers knew that the change manager didn't really understand what was written in the spreadsheet. So, they just copied and pasted, and the change managers knew that the developer knew that the change manager didn't understand what was in the spreadsheet. And so what you have at this point is what I like to call risk management theater. It's a performance designed to give the impression of effectively managing risk while actually making things worse. What you actually want is real data that shows what happened to a change, the tests that were run against it, the results of those tests, the exploratory testing results, and so forth. Not a piece of paper or a spreadsheet that says that you did some things which you may or may not have done. That really is about making sure that when something goes wrong, I can say, well, it wasn't my fault because, look, I filled in the spreadsheet. One of the things that I've been working on, I spent the last year working for the US federal government. And the US federal government is probably the most regulated industry, certainly that I've experienced. To take a moderate impact system and put it into production, you have to implement 325 security controls. And you have to produce something called a system security plan, which lists and describes exactly how you implemented those 325 security controls. And it typically takes between 6 to 9 months just to do that documentation and then fill in another report that shows that that has actually been tested correctly. So to go from dev complete to live takes typically 6 to 9 months in the US federal government just to document and then test those 325 security controls. So I was working for kind of a startup within government called 18F. The people who fixed the healthcare.gov platform went and helped to co-found this team in the US government. And we decided that we had a way to help with this problem. What we actually ended up doing is building this thing called cloud.gov. which is built on open source tools. It's built on open source Cloud Foundry, and you can actually go to GitHub and download the source code and stand up your own instance of cloud.gov. So it's Cloud Foundry built on Amazon Web Services. And what we realized is we could take care of most of these controls at the operational layer so that the developers didn't have to care about them. Many of these controls are about networking and data centers and things that are below the level that developers care about, but developers had to re-implement these controls for every system they built. So actually, we can take care of a lot of these controls at the infrastructure layer and at the platform as a service layer. Amazon has put a lot of effort into making sure that they comply with these regulations. And there's a special region of Amazon Web Services called GovCloud, and they've actually documented in their system security plan how they implement a large number of these controls. We realized we could take care of a number of these controls at the platform layer too. And so we actually got our certification for cloud.gov in February. It was approved by the CIO of the Department of Defense, the Department of Homeland Security, and the General Services Administration. So it's now authorized for use by federal government agencies. 269 of those controls are actually handled at the platform layer. And then there's 41 shared controls, but only 15 controls must be implemented by the customer. That substantially reduces the compliance burden of app dev teams that want to deliver to the cloud, because you can take care of most of those security controls at the cloud layer. So this is just one way that you can actually use modern DevOps and continuous delivery practices to improve your ability to meet compliance and improve your ability to handle regulation. And we deploy cloud.gov. I mean, we have deployment pipelines for cloud.gov. We make changes to the cloud.gov platform at least every day, sometimes more frequently, using continuous delivery, using deployment pipelines, because that actually makes things safer. Now I'm going to talk about something a bit different. People think that continuous delivery is about websites. That's not necessarily true. One of my favorite examples of applying continuous delivery principles and practices comes from firmware. This is a bit weird because typically people don't update their printer firmware 10 times a day. So why would you care about continuous delivery if you're building firmware? That seems like a strange decision. So I'm going to tell a bit of the story about HP LaserJet firmware. In 2008, they had a problem, and the problem was they were going too slowly. In printers, you have very complex custom chips called ASICs, and it takes 1 year just to fabricate the chips. So you would think that would be the critical path. If you want to build some new printers, well, we have to fabricate the ASIC. That's going to take a year. That's going to be the thing that takes the longest amount of time. Well, it turned out it was the firmware that was the critical path. That's how you know something's really badly wrong with your software process. I once did some work for a European airline. It was going to take, so they were installing premium economy. So these are where the seats, you have slightly more legroom. It was going to take them longer to change the booking system to book premier economy seats than it was going to take them to change the seats in all the aircraft. So again, if software is your critical path, that's when you know things are really bad. So firmware was the critical path in new printers. They tried everything. They tried outsourcing, they tried insourcing, they tried hiring people, they tried firing people. In the end, they were so desperate, they asked the engineering management for help. That's how you know things are really bad. And so the engineering management did something a bit different. They looked, instead of at cost accounting, typically people are like, what's the most expensive thing? Let's reduce that. They did something called activity accounting. Activity accounting is looking at the activities that you're spending your money on. And they didn't do it to a very high level of precision. They just got a rough idea of where they were spending their money. They found they were spending 10% of their money on code integration, 20% of their money on detailed planning. The product team had this big list of features, and they would go to the developers and say, these are the features we want to deliver in the next year. And the engineers would laugh at them and say, pick the top 2. And then the product people would get really, really mad and say, prove to us why you can't deliver any more features. And so they would be spending enormous amounts of engineering effort doing very detailed estimates to prove why they could only build these 2 features. And then they'd get about 6 months in and realize they couldn't even build 2. And then they'd have to do a very detailed replanning to prove why they could only do 1 of those features. And that was taking 20% of engineering budget was just spent on planning activities. Every time they released a new line of printers or devices, they would take a branch of the code, so basically a complete copy of the code base, and start developing for that new line of devices on that branch. That meant that any time they had a bug fix or a new feature which applied to multiple lines of devices, they would have to port it in version control between the branches. That was taking 25% of their costs. Another 25% of their engineering costs was spent on product support. What does that tell you if you're spending 25% of your budget on product support? Yeah, it's a quality problem, right? 15% of their budget was spent on manual testing. If you subtract that from 100%, what you're left with is 5% of your budget to actually spend on building features. Or as I would be doing, sitting down, drinking vodka a lot. But it becomes very clear the reason why we're going so slowly is because we're spending all this money on all these non-value-add activities. Who's worked for a manager and the manager says, we'd really love to give you time to do test automation and deployment automation and refactoring, but we don't have time because we've got to keep delivering the features. Anyone heard that? Okay. Well, the fallacy is really clear. The reason you have all this pressure on you to deliver the features is because you're spending all this time and money doing non-value-add activities. That's the cause of the schedule pressure. The only way to fix the schedule pressure is to remove the amount of time you're doing this so you can increase the amount of time and money you're spending on innovation. And you have to invest in order to do that. So that's what they did. They also looked at cycle time drivers. They were taking 1 week to get their code into trunk. They could only get 1 or 2 builds a day of their software, and it took them 6 weeks to do a full manual regression. So they decided to completely re-architect their system, which is kind of a risky move. But they had some key principles for this re-architecture. Number 1, they wanted to remove hardware variation. So they had an engineering department in charge of designing the physical chips. They said, you can't just choose any CPU you want. We're going to have a single physical architecture so that we can take the same firmware build and deploy it on all the different devices. And so that was an agreement they had with engineering, with the hardware engineering people. You need to reduce the variation so we don't have to keep changing the firmware for all these different devices. Then they could create a single deployable firmware package that ran on any of their physical devices. That meant they didn't have to keep taking branches in version control for all these different devices. That meant they could implement continuous integration, the practice of making every change into a single shared trunk or mainline and running automated tests and fixing the build when it broke. Then they invested in comprehensive test automation to try and reduce that 6-week regression testing period. And in order to do that, they created a simulator for their ASIC so that developers could run the automated tests on development machines rather than having to have a physical logic board to run the tests on. So this is a lot of work. They invested substantial amounts of engineering effort into test automation and creating a simulator for their devices. But even then, they had this problem with continuous integration, that some developer would check in a change and it would break the build, and then the build would be broken for hours or days. And so the director of engineering had this habit of walking around and just asking people annoying questions like, why do your changes keep breaking the builds? And the developer's like, well, we didn't know that was going to happen. That the build is finding the problem so we could fix them. And he's like, well, why is it breaking all the time? And the developers got really mad at them. And eventually, they came up with this idea. So what I'm going to show you is not what they started with. It's the evolution of 2 years of development work. But what they ended up with is a deployment pipeline that looks like this. They had 200 engineers. So this is a large distributed team working across 3 countries, Brazil and the USA and India. So, 400 people. So it's a 400-person distributed team in 3 different countries, and they were making changes to mainline to trunk all the time. Every time a developer had a change that they wanted to push into trunk, they would send it to their own special GitHub repository, and they built a continuous integration tool that would look at all these repositories and see where there was a change, and it would take that change and run 2 hours of automated tests against that change. That's level 1. If those tests pass, the change gets promoted to stage 2. That merges all the changes that have been made since the last build, and then runs all the same 2 hours of automated tests against those merged changes. If there's any problems, the developer gets an email, here's your change, here's the merge failure, or here's the test failure, and the developers can go and reproduce that on their development workstations. Only once your change has been through stage 1 and stage 2, that's when it gets put into trunk, into mainline on version control. And that's the only way for developers to get their change into trunk, is for it to pass those 2 stages of automated tests. So what that does, imagine if you're a developer. If you make 5 days worth of changes, what are the chances that the tests and the merge are going to pass? It's not going to be that high. If you make small changes, maybe a few hours of work, that means you're much more likely to get your change in version control. So what they've done is they've basically created a system that forces developers to work in small batches off trunk, because that's the only way you can get your code into trunk on version control. Then it triggers 2 hours of automated tests in level 2 that run on simulators. And then if the build passes that stage, then it runs 2 hours of automated tests against emulators. So these are physical logic boards of printers sitting in racks having automated tests run against them. They're actually sending signals to the physical logic boards and getting signals back. If that passes, then the build goes to level 4, which runs overnight on a massive grid. And so developers get feedback within 24 hours if they've caused a regression problem. And they can fix that straight away. And if you pass all of these different tests, then the firmware is considered release quality. So you don't have to wait till dev complete and then do 6 weeks worth of regression testing. You can get that feedback within 24 hours. And what that allows developers to do is build quality into the product and get fast feedback to make sure that what they're building really works. So this is continuous delivery. It's continuous integration, test automation, deployment pipelines. But it's for firmware, not for websites. And it turns out this has a huge positive impact on the delivery process. Now, it took them 3 years to do this. But after 3 years, they got budget spent on code integration down from 10% to 2%. They spent much less time doing planning. They did much less detailed planning because they were fundamentally able to deliver. Porting code went down from 25% to 15% of their budget spent on maintaining trunk. Product support goes down from 25% of your budget to 10% of your budget. What does that tell you? Better quality, right? And now we have much less of our budget spent on manual testing because it's mainly automated. Their goals, they had 2 goals for their program. Goal number 1 was to get firmware off the critical path. Goal number 2 was a 10x productivity increase measured in terms of budget spent on innovation. And what they actually managed was an 8x productivity increase. Budget spent on innovation went from 5% to 40%, so that's an 8x increase. What do you notice about these numbers on the right? Correct, they don't add up to 100% because there is a new activity. So the remaining 23% is spent on creating and maintaining the suites of automated tests. If you went to your engineering manager and said, please can I have 23% of the budget to spend on test automation, what would your engineering manager say to you? And yet, despite that, they managed to achieve this incredible increase in productivity. And what I love about this case study is they wrote it in a book, and you can buy it, and you can see it changed the economics of the software delivery process. Overall development costs were reduced by 40%. Programs under development increased by 140%. Development costs per program down 78%, and resources driving innovation increased by 8x. People think lean is about cutting costs. Lean is not about cutting costs. Lean is about investing to remove waste. And that creates cost reductions on the back end. You amortize that investment cost out the back end because it substantially reduces the cost of ongoing innovation. But it does work. The third objection that I see is, we can't do that here. We have too much legacy. People think continuous delivery is risky. I hear this a lot. Continuous delivery is risky. Who works at a company where you're running mission-critical software on hardware that is no longer supported by the hardware vendor? Okay, that's not risky. Who's running mission-critical software on hardware where you have to buy the parts on eBay when they fail? Anyone? Yeah, there's always one. Who's running mission-critical software where you don't have the source code to that? It disappeared long ago and you have to kind of patch it. Okay, yeah, right. So this is real, right? Someone once asked on Reddit, what programming language should I learn if I want to make the most money? What's the right answer to that question? COBOL. Absolutely. All those COBOL programmers retired at age 45, and they now live in big houses with swimming pools. Because anytime big financial services company wants their COBOL mainframe system fixed, they call up the programmer and they're like, we really need this fix made. And the programmer says, I would love to help you. That'll be $1 million. Very profitable. But those systems are still at the core of many banking applications. IBM has a very profitable mainframe business. As someone from IBM once told me after I gave a talk on building cloud-native systems, imagine if you had a cloud system without network partitions. At IBM, we call that a mainframe. So that was hilarious. So, too much legacy. So I'm going to show you a short video from Suncorp. Suncorp is Australia's biggest insurance company. And it's from a longer talk called From Mainframes to Continuous Delivery in 1,000 Easy Steps. And this is just the end of the video where they're talking about how they implemented a comprehensive test automation framework for their mainframe systems.
So you're going to see a little test running here. I'm going to run that, and what you're going to see here is a demo. There's a couple little mistakes, and that's okay. The green screens are remarkably durable and remarkably quick, and I found this to be an incredibly good testable endpoint. So they're kicking off a little test here, and this is actually going through an amazing number of workflows. This is creating a new company. This is and creating new contracts for that company. That generally takes an analyst about 10 minutes to do, 15 minutes to do. And what we discovered through this was that green screens are amazingly fast and amazingly durable, not just the systems themselves, but testing them is very fast. So what's going on the bottom is jobs are running, and they're waiting for the jobs to run, and then they're kicking off batch jobs to run in the background, which is quite remarkable. So what we were doing was, for supporting UAT testing, because we had this type of capability, we could set up 500 to 1,000 policies anytime we wanted for UAT to run. We could set up training environments with thousands and thousands of policies for people to learn from. But what we found, and we use Concordian, so I'm going to stop it right there. This is just an example of some of the Concordian output. But I was very surprised that GUI test works so well on a mainframe environment. We didn't think it would, but we put a lot of time into the test engineering and working with the system to make.
So you could see they actually used Concordian, and they built a little shim so that the Concordian test framework could actually talk VT to the mainframe system. And then they were running thousands of automated tests against their mainframe systems using VT. You can absolutely do this stuff with mainframes. Mainframes, it turns out, are really good automation targets. You can absolutely do this stuff. So don't let anyone tell you, oh, we can't do this stuff, we're using mainframes. Absolutely not. You can test automation with mainframes, entirely possible. What we do find, though, is the problem comes when you have mainframes talking to a bunch of other systems. And if you're familiar with bimodal IT, this is Gartner's kind of thing, bimodal IT. You know, we're going to use waterfall development on the mainframes, and then we're going to use agile development on our systems of engagement, on our front-end systems. Well, that's okay until the front-end systems have to talk to the mainframes. And then it doesn't work anymore because these things are coupled to each other, and then you have to do these big bang orchestrated releases. You can only release everything at once. You can't release independent parts of it because everything's coupled to everything else. And then what happens is you're forced to move at the pace of your slowest moving system. So 2 answers to this. 1, don't be afraid to automate your mainframe systems. That's absolutely doable. But secondly, you have to attack the architectural problem. The architectural problem of all these thousands of systems being very tightly coupled to one another. So who's seen the film Tomb Raider? Has anyone seen Tomb Raider? Okay, so this film carries important architectural lessons, it turns out. Very useful. So this is Angkor Wat, and what you can see here, this is, once upon a time there was a tree here, and a little bird came and did a poop on the tree, and in the poop was a seed for a fig, a strangler fig. And the strangler fig grew up around the tree and gradually strangled the tree and killed it, and all that's left is this strangler fig that grew up around it. So this is what we want to do to our systems. This is an architectural evolution approach called strangler application. You have some big monolithic ball of mud. And what people love to do, architects love to imagine a brave new world of service-oriented architectures, and they come out with a big blueprint. Here's the beautiful new architecture, but it's going to take us 3 years to rebuild everything. And then they go and start the big bang rebuilds of everything in this new environment. And about 1 year in, you ask, well, how much longer is it going to take? And they're like, oh, we think it's going to be another 3 years. And then another year in, you're like, well, how much longer is it going to be? Oh, we still think it's going to be another 3 years. And then eventually, a new VP comes in, or the VPs get fired, and then someone comes up with a new architectural blueprint of the new thing. So those big bang re-architectures are quite risky and dangerous, and often they end up getting cancelled. Who's been involved in a big bang re-architecture that got cancelled? Yeah, me too. So instead of doing that, what you can do is rebuild the plane while it's flying. So strangler application is an alternative strategy. Instead of doing the big bang re-architecture, we're going to gradually and incrementally rebuild pieces, one piece at a time, while we keep the whole thing working. So the rule is, when you build new functionality, you can't touch the existing big ball of mud. You have to build it in its own module using modern continuous delivery practices, TDD, deployment pipelines, all this stuff, and it has to have its own database. You can't talk to the big monolithic database. And gradually, as you add new functionality over time, you build a service-oriented architecture, and some of those services are still talking to your original monolithic app, but over time, gradually, you strangle it as you build up new stuff. And this never ends. You're going to keep doing this forever. Your systems are never going to stop evolving, because your business is never going to stop evolving if it's successful. And as your business evolves, the architecture that it needs is going to change necessarily. I just want to talk about how Amazon did this. People think that Amazon is this amazing company and everyone inside it are all geniuses and they're somehow special, but that's not true. They just have really good marketing. Actually, Amazon is the same as everyone else. They have the same internal problems. And in 2001, their database, they couldn't scale it anymore. They bought the most expensive hardware they could, and they couldn't scale. And so they decided to re-architect to a service-oriented architecture. What was interesting was that the memo came from Jeff Bezos, who's the CEO. And he sent a memo to his entire technical staff, and it's summarized in Steve Yeager's platform rant. So if you Google Steve Yeager's platform rant, you come across a really big document, which I really recommend reading. But one of the things that he does is he summarizes Jeff Bezos' memo to everyone, which looks like this. Number one, all teams will henceforth expose their data and functionality through service interfaces. Number two, teams will communicate with each other through these interfaces. Number three, there will be no other form of inter-process communication allowed. No direct linking, no direct reads from another team's data store, no shared memory model, no backdoors whatsoever. The only communication allowed is via service interface calls over the network. Number four, doesn't matter what technology they use. HTTP, Corba, PubSub, custom protocols, doesn't matter. Bezos doesn't care. Number five, all service interfaces, without exception, must be designed from the ground up to be externalizable. That is to say, the team must plan and design to be able to expose the interface to developers in the outside world. No exceptions. Number six, anyone who doesn't do this will be fired. So, maybe you read the article in the New York Times about Amazon's internal culture from 18 months ago. So, I don't really agree with statement number 6 here, although perhaps it tells you something about Amazon. But he was quite serious about this. He hired a guy who had been an Army Ranger in the US Army. And this guy's job was to go to the teams and look and see if they were trying to access other teams' databases directly instead of using service interface calls over the network. And if he found your team doing that, he would shout at you a lot. And if that didn't work, he would try and have you fired. Like, they were really serious about this. And I think this is what's different. Like, how many companies the CEO sends a memo about service interface calls being over the network, not to databases, and then hires an Army Ranger to go around and enforce that? Like, there's a degree of seriousness and discipline about this that I think is perhaps lacking in other companies that approach the service-oriented architecture, which is pretty crucial. But it took them 4 years to do this, to re-architect everything, to enable them to achieve this thing that I showed you all the way back up here. So that was like 4 years of work to do that re-architecture, during which time they didn't ship a lot of features. It's the same thing with HP LaserJet. That was 3 years of re-architecture, during which time they didn't ship a lot of features. That was a ballsy business move. I mean, that involved a lot of courage to go and say, we're not going to ship a lot of features, we're going to completely re-architect, and we're going to be very disciplined about that re-architecture. So a lot of investment, again, in order to be able to achieve that business goal. So I'm going to come to my fourth objection. Our people are too stupid. So there's a guy called Adrian Cockcroft. Adrian Cockcroft was Netflix cloud architect, and now he works at Amazon. But he led the team of people that developed a lot of the patterns for building cloud-native systems. I mean, Netflix consumes something like 30% of the USA's internet traffic. So it was a big deal. So a lot of the patterns were from him. And he talks to a lot of senior executives, and senior executives from other companies would go to Adrian and say, Adrian, where do you get these brilliant people at Netflix who can do this stuff? And Adrian turns to them and says, I got them from you. And this is absolutely true. It's the same people. They're not special. They're just in a different environment with different management practices that enable them to actually innovate more effectively. So, I mean, the problem is that people are too stupid. It's just not the people you're thinking about. So I talked a bit earlier about Toyota and the Toyota production system and the revolution in manufacturing. There's a great story about that. About 30 miles from where I live in California is a factory, which is now the Tesla factory. But in the 1980s, it was a General Motors factory. And General Motors was building cars. I don't know what model of cars, but they were building General Motors cars. It was the worst plant in the whole of North America for General Motors. Relations between the unions and management had broken down to the extent that the workers would drink alcohol during the day, they would gamble, they would take time off. It was really bad. They would deliberately sabotage the cars and put like Coke bottles in the doors so that the doors would rattle when people opened and shut them. So General Motors shut this plant down completely. Around the same time, they decided to create a joint venture with Toyota. They wanted to learn how to build small cars profitably, because GM had never been able to do that. They also heard about the Toyota production system, thought that was kind of interesting, wanted to learn about that. Toyota wanted to build cars in North America because the US government had just imposed trade sanctions on Japanese car imports because they were too successful. Obviously, the solution to that problem is trade sanctions. And so Toyota wanted to build a plant in North America so that it wasn't subject to the trade sanctions. So they created this joint venture called NUMI, New United Motor Manufacturing, Inc. And they decided to put the factory where their old GM factory had been in Fremont, in California. And then something crazy happened. GM's union leaders convinced Toyota's management to rehire the same people who'd been working in this GM plant. And so they sent them to Japan, to Nagoya, to Toyota City, to work on the Toyota production line and learn the Toyota production system. And after a few weeks of learning the Toyota production system, they came back to work at the NUMI plant in Fremont. And within a few months, they were producing the highest quality cars of any GM plant in North America, and as high quality as the cars that Toyota was producing in Japan. The same people. It was not the people who were the problem. It was the system of work and the management system that was the problem. So what's different between GM and Toyota? Well, here's a picture from a Toyota plant in the UK. And you can see along the bottom, there's these lines along the floor. And so what happens is this. You've got a production line. There's cars coming along the production line. And say you've got a job. Your job is to bolt the chair into the car, right? So the car comes along, you've got a chair, you put it in the car, you start bolting it in, and then the thread breaks, and you have to take the bolt out, and then you have to try and put it back in. But by that time, the car has gone past your cell. You don't have, somebody else has to do their job now, so you're done, you can't fix it. So now the car goes off down the assembly line with the chair not in the car properly, and there's nothing you can do about that. So what happens is they have QA. At the end of the factory, at the end of the production line, there's QA. And QA's job is to be like, well, no one can drive that. It doesn't have a chair in it. Off it goes to a parking lot. We'll fix it later. Well, this one's not going to work. The engine's bolted on the wrong way. Off that goes to a parking lot. And so at GM factories, a lot of the cars go off to parking lots to be fixed later or to rust, whichever happens first. So what's different about a Toyota factory? Well, at a Toyota factory, what happens is this. You get the car, comes along, gets some of the way along. You're trying to bolt in the chair, and about 2/3 of the way along, this line changes color. And if you're not done by this point, what happens is you can pull this thing called an andon cord, or in the latest Toyota factories, there's a button that you push instead called the andon button. And what happens is a light goes on, and a jolly little tune plays, and then a manager comes, and the manager helps you. How good is that? And so the manager, and you fix the problem, and if you can't get it done by the time you're at the end of your cell, you can pull the andon cord again, another jolly little tune plays, a red light goes on, and then the whole production line stops. And then you fix the problem, get it done, then you start the production line again, off the car goes, and then sometime later you reflect, how could we improve the process? And there's actually a whole team at Toyota factories whose job is to help you improve your tools. So you can say, well, this wrench, it would be better if we had an angle in it here, and then the engineers will go off and bring you back one, and you'll be like, oh, that's much better. Cool. So they'll help you actually implement your own ideas to improve the process. It's not the managers telling you you must do this. The people working on the production line get to come up with ideas and get them implemented. So the key is you have the power to build quality into the product. Quality is not the QA's problem. Quality is your problem, and you're responsible for the quality, and you don't let anything go downstream that's broken. And you have the power and the authority and the tools and skills necessary to build quality in. So if you want to hear more about this, it's a great story. There's an episode of This American Life called Numi that you can listen to. It's a 1-hour podcast. There's a transcript if you prefer to read it. And then John Shook has an article on how to change a culture. And what he basically says is the way you change a culture is not through a culture change initiative or program. The way you change culture is fundamentally by changing the way that people behave as they do their daily work. And this idea of building quality in, of giving the people doing the work the tools and the capability to actually build quality in, is a very old idea. It actually comes from Toyota's first product. Who knows what Toyota was doing before they were building cars? So they were building looms. They were building looms for weaving. And so this was Toyota, because the family name is actually Toyota, not Toyota. This was their breakthrough product in about 1927, I think. This was a loom where it could actually detect problems and stop. So before you had this loom, every loom had to have an operator, and the operator would just sit and look at the loom and do nothing until it stopped working, and then they would fix it. So you would have a lot of people who were very bored until something went wrong, and then they would fix it. But this loom would automatically stop working if there was a problem, like if it ran out of thread or if the thread broke or something. And so that changed the economics of the problem. Since the loom stopped when a problem arose, no defective products were produced. This meant that a single operator could be put in charge of numerous looms, resulting in a tremendous improvement in productivity. So this idea that we have a system that finds problems straight away so that we can fix them, that has a modern analog in software engineering. What is it? Yeah, it's continuous integration and test automation. So who's practicing continuous integration on their team? Okay, keep your hands up. Keep your hands up. I have a free certificate, which I will give to some of you. So keep your hands up. And unless everyone on your team is pushing into trunk on a daily basis, put your hands down. So you can only keep your hands up if everyone is pushing into trunk at least once a day. If you're working on long-lived feature branches that don't get pushed into trunk, merged into master at least daily, put your hands down, otherwise you can keep them up. Okay, if when the builds break, they are not typically fixed within 10 minutes, put your hands down, otherwise keep them up. All right, so there's 3 people in the audience doing continuous integration. Well done. You get a certification. It's really hard. Continuous integration is a practice, not a tool. It's the practice of everyone working off a shared trunk or master. And when the automated tests show you there's a problem, you don't just leave the build. If this thing says there's a problem with your loom, and you're like, fuck it, just keep the stuff coming out. Like, no, you've got to fix the build when it breaks. If the tests fail, you have to fix that problem straight away. This is a practice. You can do it without any CI tools at all. And it's the practice and the mindset that's really important. What we're trying to do is divide the labor. Computers are really good at doing boring, repetitive tasks. Humans are really good at problem solving. So what you're trying to do is get the computers to do the boring, repetitive things like regression testing, and get the humans to do the high-value, heuristic problem-solving work, fixing the problems when they happen. And it turns out that implementing these ideas is what changes culture. So I've been doing research for the last 4 years, working on the State of DevOps report with Puppet Labs. We've got some peer-reviewed published papers that you can read here. And what we find is that these practices of continuous delivery, not only do they create higher levels of IT performance, which in turn leads to higher levels of organization performance, but they also change culture. And we know that culture actually impacts IT performance and organizational performance. Continuous delivery also leads to lower levels of deployment pain, lower change fail rates. Actually, in a previous year, we showed that it leads to lower levels of team burnout as well, because if you give tools the teams to do their job well, they're less likely to feel burned out. And it also leads to higher quality as measured by the proxy variable of lower levels of rework. So I'm just going to end with a quote from Taiichi Ohno, who was one of the chief creators of the Toyota production system. Fundamentally, continuous integration is about continuous improvement. It's about all of us working every day to make things better. He says, Kaizen, or improvement opportunities, are infinite. Don't think you've made things better than before and be at ease. This would be like the student who becomes proud because they bested their master 2 times out of 3 in fencing. Once you pick up the sprouts of Kaizen ideas, it's important to have the attitude in our daily work that just underneath one improvement idea is yet another one. High-performing companies, what makes them special is that they're always working to get better. They're never satisfied. They're always looking to improve. And the way they improve is they make improvement work part of everybody's job. It's part of everybody's job to try and make things a little bit better. And so I think if you want a takeaway from this, every day when you go into work, think, what's one thing I could do to make life better for the people around me? What could I do today to make things a little bit better for the people around me? And if all of us did that every day, that will make things a whole lot better. And I'm going to finally end with a quote from Jesse Robbins, who is master of disaster at Amazon. He was head of availability. He says, "Don't fight stupid, make more awesome." So I hope all of you will go forward from today and make more awesome. Thank you very much.
Thank you very much.
Thanks.
Could you just stay here, because I can imagine that people do have questions. So if anybody has a question, I'm going to throw a box at you, and you can talk magically into the box, and everybody will hear it. Any questions? Oh,
Wow, it works, the box.
it's magic.
Yeah, I see. Well, I have the problem that my managers had a training from Jeff for a whole day. And even after that, they decided last quarter of last year, that it was not important that the new app would have CI/CD or would have test automation. And of course, the app should have been live, because they decided in September it should have been live by Christmas.
Of course.
And of course, the app is not yet live and has a lot of problems now. And they still don't see that the decision they made is wrong, and they still don't automate.
Jeff,
How
you're
can I?
ineffective. How can this happen? And what now?
Yeah, I mean, this is the fundamental problem that we face, right, is that these ideas are not new ideas. I mean, continuous integration is a 90-year-old idea that was invented when building looms. Most of the management problems that we see today, there's a great book called The Human Side of Enterprise by McGregor, which was written in the 1960s, which talks about management dysfunction and how to fix it. So, you know, I'm just the latest person talking about these ideas that are decades old in many cases. So it's very hard. Firstly, you need there to be typically need there to be a crisis. I think you're probably going to give the answer to this in your talk, to be honest.
I am. But it's
so
kind
go
of
and see his
mean
talk.
to put you on the hot spot now.
So first, people have to have a crisis, I think, a lot of the time. If you can get people to change the way they behave without a crisis, then I applaud you. That's amazing. But generally, there has to be some kind of crisis. And then they have to have tried everything else first. There's 2 fundamental ways you can get change. One is top-down, with the agreement of the management and the agreement of everyone working within the organization. You're very lucky if you can get that. The other kind is to do guerrilla change. So, I mean, one thing from the HP LaserJet story, you know, they didn't tell the managers they were going to do test automation. They just did it because it was part of their job. Like, when people go and ask the managers, can we do test automation? It's like, you know, please, okay, I would like you to fix my car. Okay, I'll fix your car. Would you like to pay me extra to make sure that it actually works when I fixed it? That's a stupid question, so don't ask it. So I would say, you know, a lot of these things, don't even ask.
Install Linux first, tell management later.
Yes. So the only problem with that is that it's hard to make sustainable change in that way. But I would say a lot of this stuff, just it's part of your job to do the right thing.
Yes.
Yeah, hi. I would like to ask you about continuous integration, especially for mobile apps. If you look at iOS, you release approval from cycle from 3 to 10 days that you cannot control. Yeah. How do you cope with these kind of things?
Well, that's exactly the same problem as firmware, right? Because the firmware is only getting released once every few months. So it's the same problem. And I used to work on user-installed software where we build a package and then it gets installed by the users. So you download it from FTP and install it. But you can still apply continuous integration and test automation. Even if you're not actually releasing the software that frequently, you can still apply the ideas and make sure it's releasable. That's the difference between continuous delivery and continuous deployment. Continuous deployment means you're releasing all the time. Continuous delivery means you're behaving as if you were going to release all the time, even if you're not. So mobile, firmware, user-installed software, the same thing. But you still achieve these huge efficiency gains and quality gains through implementing continuous delivery, even if you're not actually releasing all the time.
One last question. Will you release the slides
Yes.
continuously?
Well, these ones are out. So if you send an email to jezhumble@sendyourslides.com, you'll get an email back.
And we'll put them on the summit side.
Yeah,
as
we'll
well.
put them on the summit side too.
Okay, thank you very much.
Thanks very much.
Now, yeah, give him a big hand of applause. Hey, will you be around? Will you be around?
Yes, I'll be around all day.
Excellent. Okay, now we're going to do something very complicated. I'm going to explain you where a lot of rooms are. And the basic trick is no matter what room, but of course the central room, all other rooms are out that door. If you want to go to the experiment, turn right. Same for the studios. It's all to the right, and it has signs. It has also people from DevOn that will explain where to go and how to go. Only if you want to have chaos, turn left. And it looks a little bit like this. So, did I tell it correctly? Because I'm always in chaos as well, myself in my head. No, I did not tell you correctly. It's the studios at the 3rd floor, and the chaos is next to the chemie. And maybe for the ones who are not Dutch, if you want to talk Dutch, you need to be able to say. If you can do that, you can say chemie, and then basically you're fine. And we always practice in the Netherlands with Scheveningen. So I once had an American girlfriend, and she says I can talk Dutch because I can say. So basically you're there already if you can do that. So it's chaos and chemie, and basically those are the rooms you want to go to. Now there is a whole bunch of sessions, and I hope we have the slide as well here for the sessions, because there's a lot to choose from. And let me warn you, you will always pick the wrong session because there's so much you want to be at. In this room, Jelle Niemandsverdriet will be talking about a very optimistic subject, security is dead. This is basically the optimistic track. You know, it will end with the Titanic here, and the other one will be Rini van Solingen with Sick of Scrum. Raoul, I saw him sitting there already. How to make this offshoring thing work for your company. And Bas Peters on how you can use open source internally in your organization. Then Ad van de Ven, I did not see him yet, but he must be here definitely. Ad will be talking about how they work with SAP and managed to go to DevOps. Unfortunately, I can't be there. I would have loved to see that. And Harm Pauw on continuous delivery in 90 days. Which is kind of funny if you think about continuous in 90 days, but that's a whole different discussion. Martin de Gijzen will talk about forget the silver bullets, take test automation seriously. Listen to that one, because I'm going to repeat probably quite a few things that he says at the end of the day. And Naga Sharma, he will talk about happy chemicals lead to happy teams. I tend to agree with that one, by the way. And then the power woman, who does 2 sessions non-stop, how to simulate an office when working remote for Lisette Sutherland. And I don't know where she is at, but make your choice, get another cup of coffee, because we're starting at 11:05 sharp. And after lunch, I hope to see you all again for Henk Kool. But for now, have a very good pair of sessions, have very good coffee or tea or something else, and have fun.